All right, cool. Well, guys, my name's Tim Evans. I'm with Power Service. Travis invited us out. He's got some of our LAC units. Well, I'm sure you guys all have a few of our LAC units out there to come and do this pump school for you guys. Again, I'm with Power Service. I work out of San Antonio. This is Jeff Murchison. He's our service manager out of San Antonio. We work down in this area a lot. This is kind of my area of coverage. I'm just an area rep for Power Service down here. Try to make it down as often as I can. So I've met a few of you, not all of you yet. In fact, most of you I haven't met, but hopefully by the end of this we'll get that done. My card and Jeff's are on the table over here, so before you guys leave, or if you got to sneak out, definitely don't forget to grab those. Jeff's our service manager, like I said, so any problems you guys have, give him a call. And if he's not available, you can always call me. I've come out and tried to help Travis where I can and be of some service to you guys. But anyway, like I said, this is a centrifugal pump school we're going to do. And this is the pump we're going to use. It's an ANSI pump, a lot like the ones you guys have out on all your LAC units. Probably a lot of your transfer pump stuff kind of match this. But we're going to use this to, just kind of briefly go over some centrifugal pump principles, why this works, how it works, what's going on inside that pump. And then we're going to get into some troubleshooting stuff that you guys might run into a lot. So why the pump's not performing enough pressure, why it's not doing enough flow, why it sounds like it's pumping rocks, why am I blowing out seals, different stuff like that, and kind of just jump into that and see what's happening inside the pump, because we have a clear casing on this, so we can kind of look in there and see what's happening. It's just a nice training tool that we can use for this. So I hope this is helpful for you guys, and I want it to be helpful for you guys, so let's try to make this interactive. If there's anything you guys see me doing that you don't know what it is, or you're curious about it, or it resonates with something you're doing in the field that you're like, hey, I have that problem, let's talk more about that, just raise your hand, ask questions, speak up, any of that. Hey, Tim, let me ask you a question about that. That's how I want this to work, and it gives me a chance to stop talking too, so that's good too. But so with that being said, I'm going to go over a pump curve real quick, just a standard pump curve, which you guys should have for all your units out there, and make sure we're all speaking the same language and the same terminology, because I'm going to use some pump lingo and different stuff when I'm talking about this, and I want to make sure we're all coming from the same place. So we'll start over here on this guy, if I don't knock it down first. Okay? So this is your standard pump curve. This is a Flowserve pump curve. It's actually the published curve for this style, or for this pump specifically from Flowserve. Like I said, this is a Flowserve ANSI pump, but it's a similar ANSI pump to your Summits, your Griswolds, your Goulds. All of those are all ANSI style centrifugal pumps that are going to be dimensionally identical to this, and the performance will be very, very similar, and how they operate is nearly identical. Okay, so anything we talk about here is going to translate to all those pumps out there, all your ANSI, Griswolds, Goulds, Summits, all those guys, okay? So like I said, this is the published pump curve for this specific pump. Here's the model number, and I've kind of messed that up, and that's not helping. But anyway, this is the model number, and I'll kind of start there with this pump. It's a 2K 2x1 6.2 RV. Okay, most ANSI pumps are all going to use the same terminology when you start talking about these, okay? That first number on all ANSI pumps is going to refer to what they call the group size. Okay, they have 3 different group sizes with an ANSI, 1, 2, and 3. Just get larger. That's all there is to them. And that's referring to the size of this power end, and it limits what casing and wet end you can put on there, okay? So this one is a group 2. That just refers to the size of here, and then it's a 2x1. That's referring to the actual size of the flanges, okay? The bigger one's always going to be your suction, okay? So it's 2x1, 2-inch suction, 1-inch discharge. Some ANSI companies will flop those two, so it'll read 1x2. Doesn't matter. The big one's still going to be your suction. Still the same pump. It's not flipped or anything weird like that. So it's always big one, then small one, 2x1. And the 6.2 refers to the size of the impeller inside the casing. So this is a 6.25-inch impeller. They just shorten it to 6.2. They do the same with like 8.2 and 13, other ones that are not exactly that, but it refers to the deal. And this RV on the end of it, that's a Flowserve specific deal. You won't see that on all your ANSI pumps. they'll all have something there probably. This RV specifically refers to a reverse vane impeller, which is the style of impeller Flowserve has put in here, which is an important point that we might dig into a little bit later about when we're talking about ANSI pumps. There's a lot of things that are identical across the board with no matter who you buy from or what pump you use, and that's mostly dimensions. So your shaft center line, your foot mounts, your distance from the front of the flange to the end of your shaft, the distances between your top flange and this, all of that fits into the box that is this ANSI pump. So if you buy this ANSI size from Griswold, Summit, whatever, it'll all fit dimensionally identical in here. So the only things that really differentiate the ANSI pump lines are A, what attachments they put on, whether what kind of seal, what kind of flush plans, all that stuff, but also the internals of the pump, like the impellers. And that's going to change your hydraulics. It's going to change how the pump performs. And we can get into that later if you guys want to or if you're interested in it. But that's what this RV is a reverse vane impeller. And some of that stuff's what makes the pumps different. So as far as this pump, this curve specifically, this is the main body of what we're going to look at for the performance of this pump, okay? What we've got on the left side is what a lot of pump guys call head, okay? What that means is the pressure. That's the pressure we're actually producing here, okay? And when we start working with this pump, we're going to convert all of that head, which is measured in feet here, we're going to convert that all to PSI. And that's because that's what our gauges show. That's what we use as a lingo a lot more frequently than feet ahead. Feet ahead is kind of a pump guy thing that helps us describe more accurately what that pump is doing, but it doesn't always translate to exactly what we have in the field and what we're reading on our gauges and our transmitters and all that stuff. Okay, so we'll translate that. And an important note here when we're talking about the head or pressure of what a pump is doing, I've got delta head written on here. So that's the difference of the head, the differential pressure. So that's really important when we start talking about what this pump is doing, because we need to not just look at what your discharge gauge says. We need to look at what your suction is doing and your discharge and take the difference between the two, because that's what your pump curve is going to reflect. It's an absolute from the negative to the positive or from the positive to the positive. So for instance, if we're reading positive 10 PSI here, so we're getting a positive from somewhere else, and then we're reading 20 PSI here, the pump isn't doing 20 PSI of pressure. The pump is only doing 10 because it's getting to use this 10 PSI here. The differential between the two is only 10 PSI, okay? So we gotta remember that when we start looking at our pump curves and trying to troubleshoot where we're at on our curve, okay? That'll get you into trouble if you don't know what this is and you're trying to figure out why your curve doesn't match what your pump is doing, okay? Across the bottom, we've got flow or volume or capacity. On this one, it's measured in gallons per minute. A lot of what you guys probably use is barrels per day, barrels per hour, that kind of stuff. But your curves will be in gallons per minute, or hopefully you've got a pump guy that'll convert that for you so you have a barrels per hour, barrels per day. And we can always do that. We're going to use gallons per minute because that's what our flow meter is going to read in for this demonstration anyway. Okay, we've got some other markings on here that we'll kind of go through, but just your normal pump curve. You always want to look for this design point if you have a curve that's specifically tailored for your pump, and it'll either be a red triangle like this or a big X or a spot on that curve, and that's where it was designed to run. That doesn't mean that's where it's running. That's just where the engineer, pump guy, or whoever sized it to run there, okay? And the line that goes through is the true designated pump curve for what you have there, okay? So this pump should be a slave to this line, and that's something we're gonna use as a diagnostic tool, or you guys should be using as a diagnostic tool for what's happening out there in the field. And we'll kind of demonstrate that later when we turn this pump on and start messing with it, okay? So if you're running at 60 hertz and your pump is in good condition, it should be running somewhere on this line, okay? A few other lines we got on here that are going to reflect what this pump can do are the minimum and the maximum curve that look very much like your designed pump curve, okay? And what those refer to is the minimum impeller diameter and the maximum impeller diameter that we can put on here. That's the easiest way to change a pump's performance as far as just getting our head wrapped around it, is changing that impeller diameter, okay? So if we want to run up here at this point up here, this pump can certainly do it. It's within the minimum and maximum range of what this pump can do. So if you want to run at 35 feet ahead and 40 gallons per minute, you find that spot on your curve, and then you got to try to figure out what impeller size is going to allow you to do that, okay? So we're at 6.25 at the top here. This is 5.31, so that's probably somewhere around 6 inches for your impeller. And if we need to be exact, you should be able to call your pump guy, call somebody like me or Jeff or somebody, and they can run this on a computer program and simulate what that needs to be or should be, okay? So we can do that and change your impeller diameter to suit where you want to run. Other things that might cause you to not run on that line are a VFD. A VFD acts the same way as trimming an impeller or similar to, because it slows down that impeller, and you can move down on the curve with a VFD by slowing it down and reach some of these areas in here, okay? But we're not going to run a VFD, and I think a lot of your guys' LAC units and stuff aren't on VFD, so we're going to leave that alone for now. But there's our minimum 3.5 and our max. So other lines we're going to deal with that are on your curves, which, by the way, I should specify, not all your curves are going to look identical to this. They might have this power curve down here, or they might have this NPSH line somewhere else. But what's important is they will all have this information somewhere on that curve. Or you need to call your pump guy and get it, and it'll help you solve your problems out in the field better. So other stuff we got here, this one is called an NPSH line, okay? That stands for net positive suction head. That's one we're going to deal with a lot when we turn this pump on, and it's going to be a common source of a lot of problems in our industry, especially at the wellhead, dealing with pump tanks and facility design and those things with what causes a lot of pump problems, okay? So that's net positive suction head. In this scenario, net positive suction head is rated as a pressure here, or feet of head, as the pump guys will call it. And if we're talking about feet ahead, okay, we're talking 30 feet ahead right here. What that actually means is a column of water. How many feet tall can this thing push that until it can't push any more pressure? That's how the pump guys actually define that feet of head, okay? And they can do that on this end and this end, okay? And on this end, it's really easy to translate because we got a tank right here. And it has so many feet of water in there. And we can calculate the surface area of that water, how much ambient pressure is pushing down on it, the weight of that water, and how much gravity is pulling down on it. And that gravity is going to push it through this piping, and it's going to end at a pressure here. That water is exerting a pressure on that transmitter because of the weight of that water in there. That is our net positive suction head. Okay? And a few things we're going to talk about that are a difference is this is the required amount of net positive suction head. It's not a result of the pump's performance. It's a requirement to run at that point on the curve. Okay? So if we're looking at our design point, which is about 22 feet of head at 37 gallons per minute, okay? That's where we want to run at, okay? If we got this pump curve in front of us, when we decide that's where we want to run, we should slide down on that line and see where we run into that NPSH line, okay? Where we intersect that. And then our NPSH numbers are over here. We slide over and we hit about 3 feet ahead is going to be required to run at that point. Okay, then you need to compare that to what you actually have in your tank. And you'll hear a lot of us pump guys, if we're helping troubleshoot, you will say, what's your available NPSH? Okay, we mark that a lot of times as NPSH-A versus what we call this, which is NPSH-R, required, available. Your available has to be more than what's required by your curve, or you're going to have problems. And we're going to simulate a lot of those problems and show you what it looks like. Okay? Any questions on NPSH? Sorry, what's that? Yep, that's your tank level. Yeah, and if your tank level's at 6 feet, that doesn't mean you have 6 feet of NPSH. There's actually a calculation you need to put in there for the weight of the product, the ambient pressure inside your tank, and what gravity's doing to it, okay? And something we're going to talk a lot about here, and you guys probably run into every single day dealing with pump problems, is, yeah, we can calculate what NPSH is happening in the tank, but just because it's happening in the tank doesn't mean I get it here at the pump, because everything in between there steals our NPSH from the tank because it takes our pressure. We get friction loss, okay? So it might be a clogged strainer, it might be too many elbows, it might be a berm that we have to go over to get out of our well pad, you know. All of those things take away your NPSH level and start to bring it closer to this required, which concerns us for not letting the pump run up correctly, okay? So that's NPSH. And something you're going to start seeing, and I don't want to get too deep off into the weeds here on this, but this doesn't say NPSH-R. That's what they used to say. Now it says NPSH-3. All the pump guys decided that NPSH-R and A weren't descriptive enough as to what's actually happening to the pump. They used to draw this line where you start having pump problems and causing damage to your pump, and that's where they would draw that NPSH line. Now they define it as 3% of head loss. So when you start to see your pressure decrease, your pump's inability to make that pressure by 3%, that's where they draw your NPSH required line. That's why it's labeled now NPSH3 instead of NPSH-R. But again, that's kind of off into the weeds. What you need to know is you need that much NPSH to operate your pump correctly. Okay? Other lines on our curve, this one right here is our efficiency curve, okay? That just refers to how effectively and efficiently our pump system, okay, everything from the motor to the impeller and the flanges, converts that electrical power into our hydraulic power, okay? So we're actually, there's a engineering calculation we can take to factor in what our fluid is, how much pressure we're going to use, and how much flow we're going to use, and the RPM of our pump to calculate what horsepower hydraulically we're going to need to move that fluid. Well, that's all well and good, except for we need to factor in all of our efficiency losses, A, inside the pump, and then B, with our seal drag, with the drag inside this transmission, with the inefficiency of couplings, motors, all those things need to be taken into account when we start talking about pump efficiency. Because if we calculate here, we're only probably going to need 1/4 of a horsepower to move the amount of fluid at the pressure we're using on this pump. But we've got a 2 horsepower motor on here because we're going to lose that efficiency. And if you can look here, here's our efficiency, and that's in a percentage, okay? At our top efficiency point, the best we're going to get right here on the curve, we come over, we're at like 24% efficient, okay? That's really bad for centrifugal pump, but it's because of the design of this pump and being acrylic and some of those things. So we're only going to use 1/4 of the power that comes through that and convert that to actual hydraulic power, okay? So that's what that efficiency means. And we're going to use that as a tool to show you guys where you need to run to keep this pump happy, okay? And we're going to reflect that in a percentage off of this efficiency curve you get. So we're going to call this highest point your BEP, or best efficiency point, because that's as high as you're going to get, okay? And we're going to talk about how far left or right of that efficiency mark you get. And the farther away you go, the more trouble we're going to give this pump, okay? So we're going to come back to that when we actually start abusing this pump, okay? Only other things on here that we're really concerned about are this line right here, which MCSF, that's minimum continuous stable flow, okay? That's the minimum flow mark on the pump, okay? So if we're on our curve, we run into that about 5 gallons per minute, okay? And we're going to get into that when we start doing bad things to this pump and show you what that does to the pump and how it's reflected there. The other things here are our power curve, okay? That's linear. It goes up as we go out, and we'll talk about that when we start running the pump as well. But that's pretty much it on most of your pump curves, okay, as far as the information held there. And we're going to go into it so we kind of get into some of those and show them what actually happens here. Any big questions on the pump curve, some of the terminology, any of that before we dig into the next spot? Cool. All right, now we got one we can draw on. It's a little more accurate maybe. And there's a reason we're using this curve as opposed to that one, okay? And that's because that's designed for a cast iron pump that looks exactly like this, okay? But we've put an acrylic wet end on this so we can see through it. And it also, we've changed the clearances inside the pump, which in pump world is usually a bad thing. We don't want to run off clearances and off specification. But with as much as we abuse this pump, we have to, otherwise we'll destroy it, okay? So this curve, or this pump is not going to reflect what happens on that published curve. It's going to be less. It's not going to be the same. So we've actually drawn out what this pump actually does on this curve. And that's something that you guys are going to maybe want to learn how to do, or if we can do with this pump training, is we can show you how to draw and make your own curve. And not only is that just really handy in case your pump guy doesn't give you one, or you're out in the field and don't have any cell service and need to figure out what that pump is doing, you can make your own just by graphing it on a piece of engineering paper or whatever, and see what that pump is doing. But it also helps you get a way better idea of why the pump works, how it works, what happens when you do certain things on the pump end. We're not going to do that today unless you guys really want to see how that works, because it takes up way too much time, and I think you guys got stuff to do, and I think we're only an hour here, okay? But it is a good practice, and it's a good thing to do, and someday if you guys want, we can come back and do this again, okay? But needless to say, I'll show you guys how we do it once we start the pump up. But other than that, this is our standard pump curve. Here's our design curve that we've got that I've drawn in here, okay? Here's our minimum continuous stable flow line that I showed you. Here's our efficiency curve. It's not accurate, it's more there just for representation so you guys see what it looks like and we'll show you how it affects where we run on the curve, okay? And then I've drawn in an NPSH line here just to show that where we're gonna require that. I did draw in a power curve here, but we'll go through that too. And I did change all of these numbers over here to PSI. And again, we got to remember, this is delta pressure differential between this suction gauge and our discharge gauge, okay? So, that being said, we're going to turn this thing on and show you where we're running on a few points on this curve, and I'll walk through how I draw it up, okay? So, let me open up some things, make sure we're not going to be pouring water out on the ground, because we've never done that with this pump before. Okay. Actually, before I start this thing, I should walk through our parts and pieces. So just what we got here, okay? We've got just our motor here, no big deal, standard motor, 60 hertz, 3600 RPM. This is our power monitor. It's actually going to show the actual horsepower we're dealing with and pulling with this pump, okay? Coupling guard, coupling inside there. Power end, that's what a lot of us pump guys will call this. It's just the transmission. It's the main bearings and lubrication, and the shaft goes through there. Behind there, you can see our shaft, and then we've got our shaft seal, our mechanical seal back in here, okay? And this is not going to have a mechanical seal like your guys' pumps where it's a cartridge seal. It just bolts on there, because we couldn't do that with this acrylic pump, but it's going to act the same way. And we can look in there and see what it's actually doing and still use it as a good tool. This is our casing, okay? I'm also going to call that a volute. That's just a pump term for the same thing. But this is our casing, okay? This is our discharge flange here, and our suction flange here, okay? So that's the pump parts and pieces. Outside the pump, we've got our tank. Just going to show, we're going to use it to simulate what happens at your guys' tanks or your NPSH. We've got a suction valve here that we're going to use to simulate some problems. Going through the suction, we've got our pressure gauge here showing our suction, discharge gauge here showing our discharge pressure, control valve on the discharge we're going to use to put back pressure on the pump or take back pressure off. This is our flow gauge or flow meter, okay, showing gallons per minute. We're going to read off the top of that plunger, okay, and back to tank. Other stuff we've got on here for instrumentation is this guy right here, and this is a pressure gauge showing our seal chamber pressure, okay? So that's going to reflect what's happening behind that impeller inside that back cover where we've got our seal chamber, okay? And just a note on construction of that, and I don't know if I have any room to draw that, but the fluid inside this casing has the ability and is designed to pass through into that seal chamber and then back out, okay? That's an important note here because we're going to be passing fluid and temperature and stuff back and forth between there, okay? And that seal chamber is designed to keep that seal chamber clean, cool, and keep fluid there to lubricate your seal faces. We'll get into that when we start abusing this pump a little more. And then the only other thing on here is our seal flush lines, okay? We're going to demonstrate those kind of towards the end of the demonstration and what they do. And then last is just a temperature gauge here, and that's plugged straight into our seal so we can see what our seal temperature is, okay? And as we do this, guys, it's meant to come up and look at and touch and feel and see what's going on. So especially when we start kind of abusing it, some of the things you kind of got to look real close at. So feel free to come up, take a look, get in here. I'll try to get out of the way and stand back here, and so you guys can see it. Okay. This is also a tool we're going to use. This is just a strobe light that we're going to change to be this. It's a timing light. We're going to change it so we can actually see what's happening inside that pump. Okay. All right, back to the pump being on here. See where we're running at. Why is our horsepower display not working? Well, I would think we wouldn't be running then. Don't worry too much about it. It's a lesser part of the demonstration anyway. Okay, so I just want to show you guys kind of where we're running on this pump curve and kind of how we drew this thing out. So when we draw a pump curve, we just have graph paper like that. That's all that's under here. And we just go to our pump, turn it on, see where we're running, okay? And something that's important for you guys to understand is your instrumentation, the closer it is to your pump, the more accurate it's going to tell you exactly what that pump's doing, okay? If we have this discharge pressure gauge up here at the top of this elbow, we're going to lose pressure through this valve, and we're going to lose pressure through this flow meter, okay? So it's going to read different if it's here versus here. It might only be 1 or 2 psi, but then again, it might be 20 yards down the road, and it might have a bunch of stuff in between it, and it might be different by 20 psi, okay? So the closer your stuff is to here, the better, and you got to account for that when you're out in the field and in the real world situations out there. So fortunately though, we're right here, so we're going to open this thing up a little bit. All right, so we're running at 70 gallons per minute right here, and we are running at a negative 6 psi on our suction and a positive 6 psi on here. So our differential between negative 6 and positive 6 is 12. Okay, so let's look on our curve. We're at 70 gallons per minute, and we should be able to slide up. And here's our point on the curve. It should be at 12 psi, which it's about 13, but who knows how accurate we are here, but we'll change it. So, again, and then we just change what the pump is doing and follow it backwards on the curve and see where else we're running. So we're going to actually turn down our back pressure valve to about 60 GPM. Okay, so we're right here at 60 GPM, and we're running at negative 4 on our suction and about 8 or 9 on our discharge. So that's going to be about 13 as a differential. Okay, so we're at 60, go up, here's our line, let's see where we're at. 13, 14, somewhere right in there, we're pretty close, okay? And so I would just make that mark, and then I would move it again. You guys do that to all your flow meters too, right?
That's what I was going to say. You see it happen on a flow meter, it's because that thing taped up. Don't actually do that.
Yeah, that's how Coriolis meters work, right? You just give them a little kick. That's right. All right, so I jumped down to 40 GPM here. So we skipped one. We're over here at 40 GPM, and we are at 0 PSI here and about 15.5 or 16 on our discharge. So 40, come up, slide over, 16 PSI, got our mark there. And so that's how we drew this. We just keep going down on our curve, get to about 30. We'll take it down to 20 just to jump to the next spot. Yeah, this valve's got a bad O-ring in there we haven't replaced yet. So you'll have that. But so now we're running at 0 on our suction, and let me get that back up to 20 where I wanted it to be. 0 on our suction and about 17 or 18 on our discharge. So we can go to our 20, slide up, 18, 19, somewhere in there, we're pretty close, okay? So we just mark those X's on our curve and then simply draw it in, okay? And that gives you a tool to work off of when you're diagnosing your problems out in the field. So a few things. We're going to walk through just a demonstration and simulate some common problems that you guys might run into. And the first one we're going to demonstrate is this NPSH problem, okay? And it's real common out in our industry, because we're not dealing with water most of the time. Usually it's crude, condensate, Y-grade, and all these things are lighter than water, okay? And that's something that's really important when we're talking about NPSH. The lighter that fluid is, the less gravity works on it in this tank and puts pressure here, okay? So the other thing we have to deal with is clogged strainers. That's a big cause of NPSH problems. Too many elbows or too long of pipe, or pipe that goes up and over berms and around other piping and around strainers, you know, all those little turns and twists are going to steal some of your NPSH from your pump, okay? Or just simply low tank level. So we're going to kind of simulate some of those problems. And no, open that. That's some cavitation across that valve that you hear, that humming noise. And we're going to hear that in other places, and we're going to want to listen to it because that's going to simulate some of our problems or be a clue to some of our problems. Okay? So I'm just going to start closing off this discharge valve, and that's just some air that's caught in there a little bit. Let that work through. But that's kind of what we're looking for, but that was just stuff that was caught in there in the valve. And you can start to see what's happening on here. Remember, this is a differential pressure. And you can watch these gauges as I start to close that valve. This pump still has to do that same amount of work. So we're at 60 GPM, so we should be around 14 PSI, 13 PSI. That pump's going to do that 13 PSI no matter what, okay? But if we start closing this valve, watch what happens to these two gauges over here, okay? So we start closing it. Our suction's dropping and our discharge is dropping, okay? So what's happening there is we're forcing this side to work harder, okay? The pump still has to produce the same amount of pressure. All we're doing is we're changing that pressure from what was 15 PSI here and 0 here, and we've moved that pressure down to the suction side. And it's still producing the same amount of pressure. It's just having to pull the vacuum here, which is stealing some of the pressure that we were using here, okay? So the pump's still doing the same thing. We're just changing where it happens, okay? So we're going to keep going. So we're almost at -10. And so there we start to hear some problems. Hear that cavitation start to happen.
Does that put any strain on the actual pump or counter?
I'm going to show you what it's doing in there. Okay, so you guys can kind of come a little closer and see what's happening. We're pulling almost negative negative PSI here. I'm going to slide this a little more out of the way so you guys can come up and take a look. And so what's happening, and you can see here, see all those little bubbles? Looks like we're pumping glitter, looks like we're pumping little bubbles in there. And those have formed, and they're moving through our suction here. And you can see them down inside the pump in here, okay? And then you can see them come into the impeller. And you can see them out on the pumping vanes there, and see it all congregating in the eye of the impeller. And another place you can commonly see it is if you can see into that seal chamber. All around our seal, you can see those little cavitation bubbles happening as well. And this is what a lot of pump guys are going to call cavitation, okay? This is what that is. And on your pumps, it will make noise like this too, other than all your stuff is steel and not plastic, so it's a lot louder, sounds a lot more violent, sounds like you're pumping rocks, sounds like that kind of deal, okay? So this is what is actually happening inside your pump when you hear that on low end PSH, okay? So what's actually happening here, why we're getting vapor in the bubbles, why we're getting that gas breakout, okay, is because we've decreased the pressure here, but we're still trying to move the same velocity of fluid through there. And that decrease in pressure has actually caused us to drop below the vapor pressure or the vapor point of that water, of that fluid, okay? And so when we do that, just like dropping below the vapor pressure of a propane or a condensate, you start to get gas breakout and it starts to literally boil. We've moved below that vapor point and it starts to boil. So when we start to boil water, what happens? Steam comes off as a gas. That's what this is. It's gas breaking out of the water, turning into steam, okay? So that then moves into the impeller eye, and those little bubbles congregate at that lowest pressure point at the eye of the impeller because of that centrifugal motion is caused there, that low pressure point. And then they start to move out towards the outside of that impeller, okay? As they do that, we still have 6.5 PSI on this discharge. So we're positive on our discharge. And so we move out of that low vapor point and out to a positive pressure, and those bubbles immediately collapse and they implode on themselves, okay? That implosion happens rather violently inside the pump, and that does actually start damaging your pump, okay? So what that looks like inside there, if you've ever pulled a impeller apart that's having cavitation problems, it looks like it's got a sponge texture to it, like it's got pits or been sandblasted or corroded. That's cavitation. That's what cavitation will do to a pump impeller or casing or seal chamber or your seal faces, in fact, okay? So that's what's actually happening there. And other things that are going to happen when we do that, and you can still see we've got bubbles and cavitation still collected back here in our seal chamber, okay? That's also not good. But when we pulled that vacuum, I don't know if you guys could see or not, but we were also pulling a vacuum from our seal chamber, okay? And what happens when we do that, and we'll see that on different areas of the pump as well, when we pull that vacuum, because that low pressure point at the eye of that impeller, it doesn't really care where it's pulling from. It just has low pressure and it's going to expect things to come in from wherever it can. So that low pressure happens back here at that seal chamber. That's why I wanted to make sure you guys understood that fluid will travel back and forth from inside that casing into the seal chamber, okay? And so what happens when we get low pressure inside that seal chamber is our seal faces are product lubricated, and so it's basically got this water in this case. In your guys' case, it might be oil, produced water, whatever it is. There's a really micro thin layer of film of that fluid in between those seal faces, and they hover on top of that, and it creates that hydrostatic seal, basically, okay? And as we pull that vacuum, we're pulling that fluid out from inside those two faces of that seal, and starting to pull gas and ambient air through those seal faces, okay? And so what happens then is, A, our seal doesn't have its lubricating fluid, so it'll start to run hot, which is obviously bad and burns up seals. Or it will actually take that lubricating fluid away from them, and they'll bounce off of each other and make contact, as opposed to floating on top of that product layer. And so that'll crack them, chip them, cause all sorts of problems, sometimes catastrophic, and cause premature seal failure, okay? So lots of reasons why the NPSH problems are bad. And again, could be a blocked strainer, could be low level in your tanks. If you're on like a truck lacked, it could be because a trucker brought a lot lighter product, which gives you less NPSH your pump wasn't designed for, and it starts running on low NPSH, okay? Any questions on low NPSH problems?
Now on a
Cool.
pipeline like that, we have one particular I'm thinking about. We've been having some problems. It looks like pulsation. So I don't know if that has something to do with.
The centrifugal pump is pulsating?
Yeah.
Okay.
So I don't know if the cause is because the downstream pump or the suction pump is causing that, or how would you troubleshoot to find that out?
What we would do is we would want to look at the whole system. We would want to look at what your upstream pump is doing, what's happening downstream. All those factors might be a cause. And NPSH is a common cause for pulsating pumps. It's not the only reason that might be happening, but it's certainly a cause of it, because it's taking what's in here and it's ramming it into that pump, and then it's looking for more, and it doesn't have it. So it'll drop pressure and it'll change what's happening inside that pump, and that'll keep happening. And it's a lot. It's not as drastic as that. Like that's like almost how you would think of a PD pump when a piston opens up and pulls fluid in. It's not as drastic as that, but that can be what happens and why it's searching for a place on the curve. Other reasons for that to be happening is possibly you have a really flat curve, which is what pump guys will call a flat curve that looks more like this. It does dip down, but not as drastically as some of your curves that have a bigger curve in them. And so what happens when you have a flat curve is it only takes just a tiny bit of pressure difference to go from this point over to here. Okay, because remember, we got to be a slave to that curve. And if we go up 1 psi, on this pump we go up 1 psi and we move that much. On this curve, if we go up 1 psi, we go from here all the way out to here. So that's a big swing. If you have a flat curve, small pressure differences, again, on the suction or the discharge, are going to cause a big swing. And so we'd have to look at how much it's pulsating and what might be the cause. But we'd love to come take a look at it. You know, we can. Yeah, absolutely. And that's the thing. When you're running pumps in series, so you've got one pump here, suction, discharge, and another pump here, and this one is running into that one. So this pump pumps into that one, okay? Those pumps need to be sized together. Maybe not identical, but there need to be spots on those pumps where they overlap, okay? And depending on which pump it is, like for instance, we run a lot of systems for saltwater disposals or tank to pipeline situations where we've got a charge pump like this, which is a small, relatively cheap piece of equipment, and then we've got an expensive pipeline pump, okay, like a horizontal centrifugal, like a Retta Schlumberger or a Barrett's or a Wood Group. Those are all examples of the same thing. Horizontal multi-stage, big, expensive, $150,000 pump, okay? We need to make sure we take care of that big pump, okay? So what we do is we will oversize this charge pump to where, by volume, not pressure, because we're more concerned about making sure there's enough volume for that bigger pump. Otherwise, this pump, if it can't keep up, that bigger one's gonna pull volume, and it's gonna either run this one out on the curve to where it's not happy, or it's gonna run dry and run into these exact NPSH problems we're talking about here. So when you have pumps working together, either in parallel, running the same direction and going into the same pipe, or in series, pumping into each other, yeah, they absolutely have to work together, because one pump can very easily outrun the other one or not provide enough and cause problems. And PD pumps and centrifugals are kind of infamous for working against each other at times. So that can certainly be a problem on either side of it, discharge or suction. Okay? And that's stuff that, guys, we're more than happy to come and take a look at. Me especially, I'm free of cost. I'm just a salesman that comes out and tries to help. I'm more than happy to come out and kick the tires and look at some equipment and try to help. Or if you have it on paper and you have, hey, this is what this pump is doing, hey, this is what this pump is doing, email it to us. We're more than happy to take a look at that and just try to be of assistance, you know. So I'll continue and we'll get after it, but great questions. Feel free to stop and ask any more, any other stuff we go at. Okay, any other NPSH questions at the moment? Okay, cool. So we've shown NPSH, and guys, what that was is we were running at 60 gallons per minute way out here. And if you'll see on all your curves, NPSH increases as you go farther out on your curve. And it should make sense because we're moving more fluid and need more supply to do it, okay? So it's going to increase. So what happened was we're running at 60. We need this much NPSH on our curve to run there. That's why it's required to run there. We dipped below that by cutting off this suction valve, okay, and ran out. And so that's what caused those problems. So that's how it looks visually on your curve. You're below that line, despite the fact that you want to run here. Okay? All right, we're going to show, remember me talking about that BEP point, the best efficiency point, and why we don't want to run off of it? That's what we're going to do now. We're going to run off of that BEP point and show you guys what happens there, okay? And there's points on that pump guys will tell you to run at or stay away from, and like the API pump guys with big, expensive, between bearing style pumps, okay? They're really good at defining those points. So for instance, they'll tell you from your best efficiency point. By the way, once we talk about BEP instead of your actual pump efficiency, our best point is 100%. That's 100% of our best, okay? This is 0% of our best. This is 100% of our best. So we're running in between there. So if we go over 100%, we start working this direction on the curve. If we go under 100%, we start working this way, okay? So we can just call that 100, okay? And let's just call this 115, 85%, just as a visual. You know, those aren't actual numbers for this curve, but it helps us get a visual. And those API guys, that's the two numbers they use. You want to stay at a window between 85 and 115% of your BEP, your best efficiency point, okay? And outside of there, you start to cause problems. And when we start, we're going to do two things. We're going to run out this way beyond that efficiency point, and we're going to run back this way on the pump curve on our efficiency point and see what happens, okay? And we're going to call those two different things. One is run out. Run out is when we go out this direction on the curve. We call that the pump running away with itself or running away with fluid, you know, those things. And then we're going to call this one backing up on the curve when we go left, or call it left of curve. And pump guys are always going to call this right of curve, left of curve, okay? Or running into high DP. Different things pump guys will call that, okay? And another thing, when we're talking about that percentage, that efficiency, they usually put in a percentage of that on the minimum continuous flow line as well. Like that's usually 12 or 10 to 15% of best efficiency point is when we hit that minimum continuous flow line. Okay, first we're going to do run out, okay, and show you what that looks like. Okay, so how we get there is basically a low pressure situation. So that's maybe you're pumping into an empty pipeline, or God forbid somebody backed into your piping and knocked a hole in it and you're pumping just out into the ground and lost all your back pressure. Or maybe you've got a control valve that's stuck open when it was supposed to be adding back pressure to your pump. Any of those things might cause this low pressure situation on the outside, or, like we were talking earlier, a pump downstream outrunning your supply pump. All those things cause a decrease in pressure on your discharge and therefore an increase in your volume, okay? So when we're going to open up our discharge. Okay, so we're running about 75 GPM now at this point, okay? So where that's at on our curve is off of our curve, okay? And that's what happens a lot at run out, and you guys will see this. You'll pull up your curve and go, well, I'm not even anywhere on this thing. I'm way out here somewhere in la-la land. Well, that's a big indicator you shouldn't be there. That pump curve is an operating window that you need to try to stay within. So we're running out here somewhere at 75 GPM. Okay, and so let's look at what our pump is actually doing here. We're pulling a -8 on our suction, and we're doing only 4 PSI on the discharge. So our differential is about 12, which isn't too far off of our operating window. But again, we're out here at run out, okay? So again, this is kind of our operating window on the best efficiency point, 85 and 110. We've gone way beyond that to the right of curve at run out, okay? So what's happening inside the pump? And this can be sometimes hard to see, but basically what you'll see inside the pump there is it looks like you're pumping little bits of glitter out there towards the end of the impellers, okay? And it's a little hard to see sometimes, and again, that's because this pump has clearances that aren't super forgiving, or they are super forgiving. But those little tiny bubbles, and you'll usually see them back at the seal chamber as well. Okay. Yeah. Yeah. Exactly. Right. And if it goes backwards, then you know exactly right. And so, what's happening with those little bits of glitter? Those are the same cavitation bubbles we were having here at the suction. They're just a lot smaller because they're happening at a lot more micro level here at the discharge. But what's actually happening is we're running at 75 GPM. Earlier, we were running real happy at 25. So we've got 3 times the amount of volume running through the same little confined space here. So we've increased our velocity around that pump greatly, okay? And the inside of that pump, let's see if I can draw this here. There's your discharge right there, okay? Your impeller is actually offset, okay? There's more space over here on this discharge end between your impeller and your casing than there is right here on this side, okay? And that happens all the way through, and that's kind of it's a scroll shape is what they call that. So it unwinds this way, okay? So what that does is it causes different velocities inside this pump at different points. It also causes different pressures inside there. It's what creates that. But at these really small clearances out here towards the tips of the impellers and this increased velocity, it's basically increasing the velocity to a point where the water and the pump can't handle it anymore and it starts to run unstably. And what it does is it causes low pressure points because of that increased velocity on the outside of that casing and on the tips of those impellers. And that's that little glitter spots that we're looking at is little gas bubbles breaking out because we've increased the velocity so much. And then again, it happens on such a micro level, as soon as they move away from that small low pressure point, they again implode, collapse in on themselves, and cause more problems for our pump, okay? And so when we take that pump apart that's been running at run out, what we're gonna see is that same cavitation pattern of looking like a sponge or pitted or cratered, but it won't be at the eye of the impeller like it was when it was NPSH problems. It'll be out at the vanes, the tips of the impellers, okay? And that's because that's where that'll be happening, okay? So that's run out. And another common couple of things that you will see at run out that I'm sure you guys have run into is remember, the farther we go out this way, higher our NPSH goes. So we're gonna be pulling a lot more here. So often you run into NPSH problems when you're running out here, okay? Other problems are, this is a simulation of our horsepower curve here. Again, as we go out farther on that curve, our horsepower increases. Often you'll trip your motor because you don't have the horsepower to do what your pump is trying to do, and you'll trip your motor out, okay? And that's something I was hoping to show you, but it looks like my horsepower monitor has broken. But it's kind of counterintuitive. My brain, when you say, give me more pressure, wants to say, we need more horsepower to do that. On a centrifugal pump, that's not accurate, okay? And you can see that on here. As we increase in pressure, we have to move this way on our pump curve, which shows if we go the same direction on our power curve, it's less power, okay? And that's because the work being done by this pump is actually being done by moving the volume as opposed to the pressure. The kind of ways I like to think about it is lifting a weight from the ground. If we lift a weight from the ground and put it on this table, like a 10-pound weight, the work is actually moving the volume, the mass of that, okay? The height is not as big of a deal because I can move it here, a 10-pound weight, and it's work. I'm doing work to do that. And it's going to take more work to put it up on this level here, but not a lot more work. But if I increase that 10-pound weight to a 50-pound weight, that work that I have to do has increased greatly compared to how much it is just to move a 10-pound weight up there, okay? So the weight or the volume, the capacity, moving more of that takes more power and increases our horsepower, okay? And that's something we can show on that typically, but again, we've broken. And this is actually what it looks like. We run at 0.8 over here on the left end of the curve, horsepower, and towards the end we're running at 1.3, okay? So that's run out. Any questions on run out before I change to the next spot? Okay, so now we're going to do the opposite, and we're going to tighten our discharge, and we're going to move backwards on the curve, left of curve, to where we call minimum flow, high DP, left of curve, all those things. And we're going to, again, escape our best efficiency window and move out of that towards the back of the curve, okay? Again, this one could be caused by blocked discharge, maybe somebody accidentally closed a valve, maybe you've got a blockage like hydrates or paraffin, different buildups, things like that might be causing this. Faulty valves, something failed close, all those things can be a cause of that. And you'll see as we pinch our valve down, we're increasing our pressure here and we're losing flow, okay? That's what we want, or that's what we're trying to demonstrate, okay? So we are at 10, we'll creep it down a little bit and just make sure we don't touch. Wow, got some bugs or something in there floating. Okay, so we are running extreme left of curve, or as close as we can get. You can see we're running at 19.5 psi on our discharge, and we're running at positive half psi on our suction. So we're running at 20 psi somewhere over here at less than 10 gallons per minute. So we're running far left of curve, and we're behind my minimum continuous stable flow line, that MCSF line. Okay, and that's really important to take note of. Anything as we approach that minimum continuous stable flow line starts to get you in trouble. You don't want to be near these extremes. Okay, sometimes we don't have a choice out in the field, we got to run. But as the closer you get to that, the more we have trouble. And that trouble starts as soon as you leave this proper operating window. That's an important thing to remember. Just because we're not out here off the curve doesn't mean we're not having some of these problems, even on a more small scale. Same on this end, okay? So what we're running into as a problem here is the pump's inability to run efficient enough to turn the power it has and the centrifugal action it has into hydraulic power to move that fluid out of the pump. We're running into the maximum amount of pressure that it can build because of its construction, okay? So what's happening is we end up recycling a lot of that fluid inside the pump, okay? And where that happens most is out here towards the outside of our pump, because that's where we have the space to do it, and that's where we're trying to put the most energy on that fluid with the outside of the pump vanes, okay? And again, this is going to look real similar to our run out problem, if it'll show us. So, and you can see it in there a little bit, but it's kind of faint with this light, and then also just because it doesn't show very well. But we're going to look like we're pumping glitter out there towards the end of those vanes as well. And again, the clearance of this pump kind of make it hard to actually put this pump in that situation, because it would also damage the pump a lot. But it does give us a pretty good idea of what it starts to look like. And we start pumping glitter out there towards the end of our impellers. And so what's actually happening there, sometimes it's called vortexing, okay? So what happens is out here at the tips of our impeller, okay, our impeller looks like this, we'll start to create little whirlwind recirculation points where we're actually causing little vortexes inside that spacing in between the casing and the impeller. So those do the same thing. They increase the velocity because it's the same amount of fluid going round and round, and they can't escape. So we're just building pressure against nothing. Causing those vortexes causes low pressure points, again, causes that same cavitation, okay? And something else that happens during this that we haven't touched on, I'll stop abusing my pump a little bit, is, again, I told you the velocities and the pressures inside this pump, because it's a scroll shape, are different on different points of this casing. So we're going to have more pressure here right next to the discharge than we are going to have over here on this side of the pump. Okay? And those uneven pressures, when they reach extremes, start moving that shaft, and we start getting shaft deflection, okay, because of that unevenness of pressure. And so when we hit those extremes, either on run out or on high DP, that shaft starts to move more. The more that shaft moves, the more we have problems, because we start having bearing problems because we're moving that shaft, vibrating that shaft. We have premature seal failure because we're moving that seal. Again, anything that doesn't want to move. And then we also start wearing out other clearances inside the pump that just keep that shaft where it's supposed to be, to the point where you can also break a shaft off if you're in really extreme situations. So shaft deflection, premature impeller wear, casing wear, rear cover wear, premature seal failure, all those things are common problems that we see when we start running on the extremes of these pumps. Okay? Any questions on that, running on those extremes? Okay, I got one more deal I wanted to show you, and that's these seal flush lines that we've got here. Okay, we've got two of them shown, and we've got a temperature probe that's reading off of our seal there. And one thing I wanted to see, no, we don't have any right now. So we've got two seal flush plans in here. And this is something all pump guys will speak this same language. You can tell them when I tell you here, and they'll all understand it. This one here on the back is called a Plan 11 seal flush, and that takes a tap from your discharge, so your high pressure end, and it brings it back to the flush port in your seal, okay? And all of your seals will either have a spot that's marked flush, or your drawing for the seal will tell you which one is the flush. Usually it's the one on top. And so we've only got about 8 psi on our seal chamber, and we've got about 19 psi on our discharge here. So when we open that up, it's going to flow from the high pressure to the low pressure in the seal, okay? So we can watch what happens here on the pressure. We're running about 96 psi, and you can also watch what happens here when I open it up, is we're going to increase pressure there. And I need to open this up a little bit. Okay, so we were running at 96. We're already dropping down to 94 and a half and almost 93 now. So what it does is it immediately starts cooling that seal, okay, by moving this in and flushing that fluid through there. Because even as much as I told you, we do have fluid pass from this casing into that seal chamber. It's not a lot. It's a very tight clearance. And so if we open this up, we open up a whole lot of fluid moving through there. And this is a more common setup we see in our industry. And the reasons for that are because it creates a positive pressure inside that seal chamber. Okay? Like I showed you, it increases that pressure there. And so what that does is it stops any fluid that comes in here from passing in through there into that seal chamber. We want to keep that seal chamber as clean and cool as we can, because we deal with a lot of paraffins, we deal with a lot of wax, we deal with a lot of frac sand. All of those things are going to be enemies to your seal and your seal face and its longevity. Okay? So if we can keep that positive seal and keep that stuff pushing out away from that seal, the better. And that increased pressure allows us to do that. Okay? The other seal plan we have on here is a Plan 13, and that goes from our suction back to the flush on the seal. Okay? And on our suction, we are at 0 psi, pretty much, maybe -1. And we already looked, we're at 8 psi on our seal. So we're actually going to go the opposite direction. We're going to go from our seal chamber out of our seal flush into the suction. Okay? And so you can watch what happens on that one. We're at 94 and a half. We open it up, and we immediately start dropping back down again. So it's another seal plan that can flush your seal. It just goes a different direction. Okay?
The fluid is coming, I guess, from the suction, and it goes past the chamber where the seal is, and then flushes it back into the
and it goes back into the suction, exactly. That direction is going this way, from the seal to the suction, right? So yeah, this fluid goes into the pump. Some of it will slide back into that seal chamber and then back out, okay?